I think we can start. It's 5 minutes past
Mhm.
5 in Moscow. So good afternoon, everyone. Uh, Welcome to the Moscow Telecommunications Seminar. And today we have a very bright speaker, Boris Bellalta from Barcelona, from UPF. Boris is a full professor and deputy director at the Department of Information and Communication Technologies at UPF. And so I hope actually you all have read his bio, and I would like just to say one thing. So Boris was the chair and the founder of the conference where I presented my first work. So actually it wasn't my first work at international conference, but it was my first presentation at the international conference. So that's why I double glad to have today Boris at our Moscow Telecommunications Seminar. So also Boris does a lot of research on topics very close to what we do in Wireless Networks Lab at ITP. So that's why I hope that today's talk on future Wi-Fi, on actual Wi-Fi 7, which is currently under development, will get a lot of interest from the audience and ask your questions. So I think that's all for the introduction part. So Boris, the floor is yours, please.
Thank you very much, Evgeny. First, thank you very much also for inviting me to be here. It's a pleasure to be able to give this seminar and to talk and discuss some of these things that I guess both you and we are basically working on. So it's a big pleasure to be here. And Jenny, yeah, I remember you from 2010 in Barcelona. I'm not sure exactly what, but could it be something about NS3? I mean, that you were presenting a paper on I don't remember exactly the topic, but I remember it was about NS3, but I may be wrong. But yeah, I remember.
You're right. You're right. It was the study on mesh networks with NS3.
Okay, okay, good. So yeah, it was a very nice event, but 10 years ago. So time goes fast. Okay, so well, this talk initially I thought, since we are doing some tutorials in some IEEE conference like GlobeCom, ICC on Wi-Fi 7, well, let's reuse those slides and yeah, give you a tutorial, a primer on Wi-Fi 7. But then, I mean, when I really thought, okay, I have to talk something to some people that may know even more than me than what is about Wi-Fi 7, better not to focus on basic things and go to some of the results that we are obtaining. Indeed, there is some introduction to Wi-Fi 7, but I will be very brief on that, and I will move to some of the results that we are recently obtaining, and in this case on a single topic, which is multi-link operation. So in that sense, let me first, well, the first slide was about me, but it's fine. I mean, everything that the introduction from Evgeny was that, so was perfect. And yeah, just you have here my contact, just in case, feel free to contact me or regarding the talk or any other thing if that's the case. So, but let me first introduce UPF and the department. UPF is a public university in Barcelona. The name is Universitat Pompeu Fabra, where Pompeu Fabra is the name of a person. This, at least in Barcelona, is not very common. All public universities usually are University of Barcelona or University Politècnica, University of Barcelona or whatever. But in our case, we have the name of a person, which was well, a linguistic from last century, which helped to develop the Catalan language and these kind of things. But many people think that we are a private university, and this is not the case. Anyway, we, as UPF, do teaching in social science, economics, medicine, and other fields, and also in computer science and telecommunications. Those two degrees are part or are taught by my department, which is the ICT department, where apart from teaching, we do research in 5 areas: multimedia, computational biology, artificial intelligence, brain and cognition, which will be the natural intelligence against the artificial intelligence from other groups, and also networking and communications. Overall, we are not a big department. We have 43 faculty members covering all those areas, and the networks and communications is one of the smallest. So we are not really big in terms of people. There's also some postdoctoral, we have some postdocs, and probably the most important thing, or the highest value of our department, is that we manage to have a large number of PhD students. And this is because basically we involve PhD students in the teaching. We have a good PhD scholarship program, which we use to fund those PhD students. Regarding my group, well, it's a wireless networking group. We are a small group. There is one faculty, which is basically me. Now there is one postdoc, which is using, well, he just arrived a few weeks ago and will be with us for 2 years. And now we are 4 PhD students. We work on wireless networking, mainly in unlicensed bands, and we don't work in unlicensed bands because we like Wi-Fi, we like it, or because we think that there is a lot of business in those bands. Especially, I like to work there because of this decentralized nature of those networks, and especially because the uncertainty that you have when you have to design. There is a lot of uncertainty when you access the channel. Once you have transmitted, what will happen with your packet, that probably in licensed bands, since you have full control of the network, will not happen. And that makes you have to design everything taking that into account, because otherwise will not work. So this is the main motivation why we work on Wi-Fi, basically. We do also some work on wireless sensor networks, but we are not pushing far. We are not pushing more on that direction, because maybe you can disagree, but I see every day more. I mean, it's every time more hard to come with good ideas for the sensor network field or low power area networks and so on. But you may disagree a lot on that. This is just a feeling that I have, and we are few people, so we cannot cover everything. Anyway, regarding Wi-Fi 7, well, we are doing research on multi-link operation in multi-access point coordination, or CHOP, transmission opportunity sharing, which basically is the same, as I will explain a bit later. And another thing in which we focus is in how to include machine learning in those mechanisms, trying to improve the performance of them. Basically, the machine learning gives you a set of algorithms that, well, allow you to learn based on the experience that the system is obtaining, so you can adapt easily to different conditions. And this is something that we are tackling in our research. Also, some of the topics that we want to cover related to Wi-Fi 7 is how to integrate ideas from the time-sensitive networking community on Wi-Fi. This is something that we are not really doing anything now, but is something that at some point we may tackle. Here, for instance, in the right side, you have an access point, which is transmitting data to a station with an agent. And just as an example of our work on this machine learning enhanced mechanism, in this case, this is about channel bonding, dynamic bandwidth access. And for instance, at this point, this access point is working on this primary channel. It has to decide, it can access 4 channels, but it has to decide how many channels it will use. He or the agent may know that there is another network transmitting periodically, for instance, on those 2 channels, and then can decide for some reason that it's better only to use the primary and this channel. Later, at another transmission attempt, it may decide that it's better to wait a bit just to transmit on the 4 channels. And this is the kind of things that we are exploring when using machine learning, how to learn what are the best set of actions in each case. This is just an example, and I will not cover this on this talk, but this is one of the active areas in which we are involved. Let me say that part of this talk is not mine. There have been many contributors to those slides. And well, let me also acknowledge some of the funding sources that have contributed to make it possible. Regarding the outline, I will start with a single slide about how Wi-Fi, the channel accessing Wi-Fi. I guess all of you know it very well, but just to be sure all of us are aligned. And then, we will overview the Wi-Fi 7 objectives, the timeline, some key upgrades that are basically improving some features from 11ax that were already present in 11ax. And then we will focus on two disruptive features of 11b. Well, we have hybrid ARQ also there, but I refer mostly to multi-link operation and multi-access point coordination. Okay. About Wi-Fi channel access, for instance, here you have 3 access points. Let's assume all of them use the same channel, so they contend for transmitting their data. All of them are in the same coverage area. So basically, at this point, all of them have a packet ready for transmission. So they will start the backup procedure. And in this example, access point 1 will finish the backup first, so it will transmit. At the same time, this will cause that access point 3 and access point 2 pause their backup, which will be released after access point 1 ends its transmission, and so on. In this example, access point 3 finishes the backup before access point 2, and after the transmission of access point 3, access point 2 completes its backup and transmits the packet. This is a standard CSMA CA operation, and this example, for instance, illustrates that let's assume that the red packet is a delay sensitive packet. For some reason, access point 3 and access point 2 have just best effort data, and access point 2 has a time sensitive packet. In this scenario, we have a lot of uncertainty in the sense that in another example, it could be that access point 2 is the first access point that transmits the packet, so it suffers a very short delay. But in this example, it happens the opposite, that it's the last one, so it suffers a long delay to deliver the data. Even if this delay is okay, it's not a problem, the CSMA, what introduces is a lot of uncertainty. It's hard to predict what will happen in a deterministic way, inaccurately, in that sense. And it could be that these 3 access points belong to the same network also. So it makes somehow a bit strange that we could not do it better in that situation. So what's Wi-Fi? Well, Wi-Fi is a popular internet access, a wireless communication technology. Basically, almost all electronic device carries a Wi-Fi interface. We have nowadays more than 16 billion of devices carrying a Wi-Fi, at least a Wi-Fi interface. We know that most of the mobile traffic, 63% at least, is carried by Wi-Fi. So it's a very important player on the wireless and the mobile industry. We can find Wi-Fi networks everywhere, at home, public spaces, at work, for industrial use. So Wi-Fi somehow is everywhere. And the key characteristics of Wi-Fi is that it works in a licensed spectrum. And this is not a bad thing. On the contrary, there is more unlicensed spectrum than licensed one. So there is plenty of bandwidth to be used by Wi-Fi. And this is basically the reason why we have so big transmission rates, or so large transmission rates. Also, we already can access the 6 GHz band to transmit and receive data for Wi-Fi, which also adds more than 1 GHz extra bandwidth to what we have been using until now. For next generation Wi-Fi, well, the applications basically will request higher capacity as has been traditional until now. But now the need to provide low latency, lower delays, and reliability become really important. Indeed, the throughput of the capacity is no more a problem. I mean, all networks provide more than enough capacity for most of the applications that we expect to have in the next 10 years. The big problem is that those applications, especially interactive video, interactive extended reality, virtual reality, and so on, require deterministic or low delay, and if possible, deterministic path. And also, if we want to target industrial applications, we need reliability. We need low delay, but also a very high reliability. And very high means 99 dot many nines of successful packet transmission. So those targets are basically motivating the need of a new generation of Wi-Fi, which in this case is Wi-Fi 7. Regarding the evolution of Wi-Fi, how we have reached this point, just to mention that from the initial .11, the motivation has to increase the capacity. We have had single-user MIMO, packet aggregation, multi-user MIMO, and so on, aiming to increase the capacity. Beyond 11N, the way to increase the capacity was to increase the channel width. I mean, we allow more capacity, more bandwidth, so we can have higher transmission rates. But beyond that, in terms of the technology itself, there were not much to do. However, the focus at this point was to add more flexibility, to be able to accommodate, to make the Wi-Fi be able to accommodate better different traffic profiles, from small devices sending few bytes to large video streaming or things like that. For instance, in 11AC we have multi-user MIMO for the first time. 11AX adds flexibility with OFDMA, which is really an important addition to the Wi-Fi community. So what will be about Wi-Fi 7? What is adding Wi-Fi 7 to the Wi-Fi community? Well, Wi-Fi 7 is based basically on 11B, and 11B has the name of extremely high throughput, but it's not only increasing the throughput, as basically is listed here. The goal also is to focus on latency, how we can leverage the different mechanisms to provide or to guarantee some lower delay somehow. In any way, our first goal is to multiply by 4 the throughput, maximum throughput that 11AX can achieve. This can be easily obtained by just multiplying by 2 the number of the channel width from 160 to 320, as it is one of the things that is done, and also multiplying by 2 the maximum number of special streams supported from 8 to 16. Just doing that, we can increase the maximum or the nominal capacity from 16 to 30, from 16, sorry, 4 times from 11AX to 11B. Also, I insist on that, one of the goals of 11B is to provide support for low latency. It's not specified how, but it's a driver of the development of 11B. For instance, as we will see later, multi-link operation is a good candidate to improve, in this case, the latency. However, it's hard to provide warranties in Wi-Fi because the operation on unlicensed bands indeed. Somehow we can control our network, but we cannot control what will happen around. So it's a pretty interesting problem how a Wi-Fi network can guarantee this low latency. For instance, in the case of multi-link, well, we will have different interfaces, and the idea is to leverage the concept of multiplexing. If one channel is busy, maybe another channel is idle at that moment. So I can transmit faster the data that I have pending. And of course, in case of 11B, one of the goals is to be compatible with previous amendments, with previous technologies, but with the benefit that if in the 6 GHz band, we will have only 11AX and 11B devices, which may help to avoid many inefficient things that the Wi-Fi do to keep compatibility with lower standards. For instance, in 11AX, there is a trend of allowing the access point to schedule all transmissions, and this will be for sure used in 11B. This in the 6 GHz band could be common. Maybe somehow we will see how CSMA-CA leaves room to other access technologies in 11B also. If you have any question, comment about, feel free to participate or to mention it or to say it.
Okay, let me open the door for questions here. So on previous slides, you limited the performance of Wi-Fi networks by 4 spatial streams. Why?
No, not limited. It's just an example. So these are here just to have some values and to be able to compare 11NN, 11AC, and 11AX, just to use 4 streams, no, nothing else. Of course, 11AX or 11AC can have up to 8, so you can have higher values.
Yeah, because one of the possible direction for improving data rates is the increase of spatial streams, the number of spatial streams. And that's why, for example, it was considered by the developers of 11B as one of possible options. So that's why question.
Yeah, no, exactly.
Limited. So we will not see the room for improvement. One question. In the chart, if 11B quadruples data rate, why it is 30 gigabit per second if 11X was 9.6? So it's like a very formal question, but
that's a good question indeed. And I don't have answer on that side. And I don't know why I have here the 30 gigabits per second and not the 45. Yeah, it could be just because, well, not a typo, because it's not a typo. It was not. Yeah, I just put 30, but yeah, true. It could be more than that, more than 30. I have no answer to that. Yeah, good point.
I think the 30 gigabit per second, as far as I remember, is a figure from PAR document, which describes the project.
Okay,
by 4 times increase is more or less like what really happens.
That makes sense, to be honest. Yeah, good point. Okay. So here we have the 11B timeline, which basically the new thing is that, as far as I know, the idea is to release a first draft of features, a completed first draft of features at the end of at some point during 2022, with the idea that those features can be already well-defined, and so manufacturers can start to implement them, and so get products to the market in much earlier than if they have to wait until the end of completing the complete draft or the complete amendment, which is expected 2024 or 2025. To do that, it looks like the task group is focusing on a subset of features, which include, for instance, multi-link operation, and some others have been left for a second release. The ones in the first release look like they will be there in 11B, but there are some doubts that all of the left for the second release will appear. I don't know if you have more information on this, but this is what, for instance, multi-access point coordination For what I know, sometimes there are more interest and sometimes less interest to keep it even in the second release. I don't know. Do you have more info on that?
May I just ask a simple question?
Yes, please.
Are these results or some experimental data, or you have some kind of mathematical or some kind of other estimations for the system?
What do you mean? In which sense?
Yes, because you're speaking about the quality of the system somewhere.
Yes.
And, do you calculate this quality, or you just measure them in an experimental setting?
So you mean in particular results?
Yes.
Oh, well, we have been working. I mean, we are starting. Well, not starting because we have been working on this for a couple of years on Wi-Fi 7. But yeah, we follow traditional approach. I mean, the results that I will present here come from some experiments and some some simulations. But for sure, in terms of research, you can build models and run simulations and this kind of stuff. I mean, it's pretty standard. However, this question it's a very good comment in the sense that some of, or traditionally, due to the complexity of different of the Wi-Fi scenarios, because you have to take into account multiple VSS, they are pretty complex and analytically they are hard to model because yeah, I mean, for instance, the Bianchi's model requires a synchronization of all the devices because the backup has to decrease at the same time for all devices. When you have multi-VSS, hidden nodes, this is not working anymore. So everything becomes very complex. And then a lot of research on Wi-Fi has been done through simulations. However, those simulations now, or those simulators, are hard to cover most of the features that 11B are developing. So one of the problems here to do research on 11B is how to do it. I mean, I will talk about multi-link operation and I will show you some results, but it's not straightforward to get NS3, for instance, and say, I'm going to test multi-link operation, because to implement those features on top, for instance, of NS3, it's really a big mountain of work. I mean, it's really crazy. And I don't know you, but this is one of the problems that we are facing, how to approach research on 11B, for instance.
I'm sorry that you don't know me, because my name is Professor Stefanuk. And I made the system of mobile communication many years ago.
Okay.
Some 20 or maybe more, because my thesis was defended in 1967.
Oh, okay, good.
Yeah. And then you were speaking about some standard like 802. How could you make the standard from the experimental results? It's a little bit strange for me.
Well, we are not. I mean, we are not doing standards. So there is a community of basically that consists of the most important manufacturers and companies that they have their own technology and try to push together to define this new Wi-Fi standard. In my case, and I guess many researchers, what we do is to take the basic concepts behind those ideas and try to develop them and to offer better solutions. In that case, the standard usually gives you the framework, but there are no specific solutions on how to implement it or how to use that framework. And this is one of the topics that we cover. I mean, for instance, multi-link operation, again, it's fine, you have the framework, but it's not clear how it will be implemented. And it will be implemented in different ways. And what's the best way to do it? This is somehow the focus of the research.
Still, it's not clear for me. Maybe I'm just not very well informed. But you know, the standards that made by IEEE, they consider to be worldwide acceptable stuff. All this system in Russia operates also in according with this standard. So the standard should be a result of some more or less general theoretical study. And it shouldn't go from some experimental observation of that type or that type, because in an experimental setting, different devices can be used by. But anyway, these standards is well accepted in our country, and so the standards should be made as a standard. So it should be some like in this COVID situation, you have to test this among the million of the people if you would like to make it experimentally.
Yeah, well, no,
So
but
that's
Dear
a bit.
colleagues, my proposal is to go forward because I think that this kind of discussion can be rather long. And
Yes,
if
sure. I agree.
if you don't mind, so we can go back to this question and to this discussion after the end of the talk.
Later, yes.
Yeah.
Thank you.
that's perfect. Just let me
Let's
add
go.
that I agree with that point of the need to have some solid background to build a new mechanism. For instance, multilink is based, I mean, we could develop easily queuing models with multiple servers to show that the ideas behind multilink operation really help to mitigate delay and to increase capacity. Then from those ideas, we can build a specific mechanism and solutions. Yeah, on that side, I really agree that it's important to have solid models and solid analysis to understand what is the best way to go ahead. And I also like that part, I have to say. Anyway.
So I'm sorry for the delay. Yes, I'll stop asking.
Okay, good. No problem. I'm happy to do. I mean, good. So, so what will be the key technical features of 11B? We have classified them into groups. The key upgrades of 11 versus 11AX, which is basically to keep increasing the channel width. If in 11B the idea is to have up to 320 megahertz, especially when we use the 6 gigahertz band. To improve a bit how OFDMA is implemented on 11B compared to the case of 11BAX, because there are some limitations. To increase, as Jenny said before, the number of special streams, just up to 16. Here there is some discussion if more than 16 streams in indoor or summer scenarios give significant gains or not, but this is something that I'm not much familiar. And also to keep increasing the modulation. In this case, up to 4K QIM is supported in 11B. Likely using few special streams and with beamforming, because and in very short ranges, but the bits per symbol that it allows increases, it's pretty big, it's pretty significant. However, all of these aspects are basically upgrades, so improvements from previous technology. What is more interesting from the research side, at least from my opinion, are the disruptive features. Hybrid ARQ is a disruptive feature for the Wi-Fi community, but not so really, because 30 years ago we were discussing on this and cellular networks already have it implemented. But for Wi-Fi, at least as far as I know, it has not been considered before or not implemented. The two big contributions of 11B, however, will be, in my opinion, multilink operation, which for me it's a very interesting technology and very simple to implement somehow, and also multi-access point coordination, which maybe it's not so simple, but it changes or it adds something pretty interesting to the Wi-Fi community, just to allow several access points to coordinate how they access the medium, basically reducing contention and allowing to use more efficiently the spectrum resources. As far as I know, there is also some discussion on how to link TSN community with Wi-Fi in a way that we can improve latency. And well, TSN is mainly used for industrial applications, currently over Ethernet networks, and probably could be easily mapped over Wi-Fi, also in industrial scenarios. But there is a lot of discussion, and as far as I know, there are no clear results yet on this integration. So let's go to the key upgrades. I will be very brief on this. I have only one slide. And basically, this slide is exactly the same that I have said before. So to achieve higher transmission rates, more bandwidth, more special streams, dense modulations. This is the straightforward way to increase transmission rates. Some improvements on OFDMA that was introduced in 11AX. For instance, one of the problems of 11AX is that you have one feature which is called preamble puncturing, which allows you that in case that you are working on, for instance, a 80 megahertz channel, if you have a busy channel, another transmission in between, you cannot use the other, I mean, you can only transmit in your primary and not in the other channels, unless you can transmit to different users. So if an access point has only one station associated, or it has traffic only to one station, a big limitation of 11AX is that it can only transmit in a small channel. So to avoid this, in 11B, the proposal is to allow to allocate multiple resource units to a single user. So in that case, the same user can transmit here, but also can transmit in the rest of the channel, improving or boosting how we use the spectrum, basically. And another direction is the need to reduce overheads. If we increase the special streams, we will die exchanging channel state information. Basically, if we do it explicitly, we need that the access point ask the stations estimate the channel and forward it to the feedback and send it back to the access point, and that takes a lot of bandwidth. So again, the solution is try maybe to move to an implicit way where the access point is able to estimate the channel from uplink transmissions without requiring all this overhead. Those are the basic upgrades. And as I said before, the most interesting part, at least from my side, are the disruptive ones. Hybrid ARQ is not a new thing in the wireless networking community, but for Wi-Fi, it could be a new addition. It's not clear if it will work because the hybrid ARQ works very well when we have traditional errors in the packet, but it's not clear what happens when we have a collision, because in case of collision, we can just lose completely a big portion of the packet. So it's not so clear if it will be an effective solution also for Wi-Fi. The idea is pretty simple. We transmit one packet. This packet can be received with errors, but then the transmitter, in this case the access point, transmits again the same packet, dual retransmission, which could also be received with errors. However, combining the current reception with the previous one, we may be able to correct those errors and then consider that packet as successfully received, so avoiding further retransmission. So on paper looks pretty well. And then the two other features that are more disruptive for 11B are multi-link operation and multi-access point coordination. Regarding multi-link operation, well, for the moment, this is the feature that has attracted most interest from the research community and also from the industry, because most of the access points now are dual band or 3-band also. The same for the stations, for the interfaces at the devices. They can work at 2.4 gigahertz and, well, if not yet at 6 gigahertz band, they can also work at low 5 gigahertz and high 5 gigahertz. So we have different options different spectrum bands to use. Soon, the 6 gigahertz band will be available, and also soon, all the devices that will appear in the market will likely be able to use also the 6 gigahertz band. So in that situation, what means multi-link operation? Basically, it adds the option to coordinate the different bands, the different channels. So now we have here in the right side, we have a multi-band access point, for instance, using the 5 gigahertz and the 6 gigahertz band as two separate networks. in the 5 GHz band, there is a laptop. In the 6 GHz band, there is a mobile phone, for instance, that can use the two bands at the same time. Well, it can operate in one or the other band, but since the access point is only dual band, it is attached or associated to the 6 GHz band. In this case, well, the laptop has no, is not asking for much traffic, so the buffer at the access point is pretty empty. However, the buffer for the mobile phone is pretty big because maybe the user of the mobile phone is watching a film or whatever. Okay. What allows multi-link? To coordinate, in this example, the two bands. So the laptop, since is only single band, it can only work in one band, nothing to do. However, the mobile phone, since it's dual band, if it supports multi-link, it can receive data in the two bands, in the 5 GHz and in the 6 GHz band, and at the same time. This basically opens the possibility to apply traffic engineering techniques there. For instance, load balancing. In this case, the traffic directed to the mobile phone is distributed through the 5 GHz and the 6 GHz band. Of course, the laptop will say, okay, I don't like this. I prefer to be alone. But overall, the performance of the network is improved because we use better the resources. And with this simple improvement on what we already have, we have the devices that are equipped with multiple interfaces. If we are able to coordinate them, we should get significant performance gains. And this is the idea of multi-link operation. Here we have an example of how this multi-link solution can work. And again, we have an access point with downlink traffic. We have a station associated to this access point with uplink traffic. Both are dual band and both support this multi-link framework. They use the 5 GHz and 6 GHz band, so one channel in each band. And for instance, in this case, we have a packet arriving to the access point, which is the packet number 1. And the access point detects that the channel at the 5 GHz band is busy, however, but not the one in the 6 GHz band. So it transmits the incoming packet through the 6 GHz band. This is what is called opportunistic link selection. So we basically use the first channel that is available. Since we have multiple options, we take one, that's fine. Packet 2, when it arrives to the access point, the two channels are idle. So why not to aggregate the bandwidth of the two channels to transmit faster? We have twice the bandwidth, so the transmission time of this packet will be shorter, and we will get some gains. The same for the uplink. And in this case, for instance, for packet 3, in the downlink, as before, the channel in the 6 GHz band is busy, so we transmit through the 5 GHz band. However, in between, the station gets a packet for the uplink, and it realizes that the channel in the 5 GHz band is busy, so it transmits using the 6 GHz band. So somehow, and this has some discussion behind, multi-link may enable full duplex transmission in Wi-Fi, so simultaneous uplink and downlink transmission. Okay, this I say there has some discussion because if the two channels are close by, since an uplink transmission also includes ACCAS and control packets, and the same for the downlink transmission. So, indeed, we have in both channels both uplink and downlink transmission. We can create interference between the two links or the two channels, and it may disrupt the other communication. So this may work if the separation between the two channels that we are using avoids to create self-interference. To do that, there is the 11B community is working in two approaches: in the simultaneous transmit and receive, when this approach is supported, or in cases when you cannot use the different channels for full duplex transmissions, so you can only use for receiving or transmitting, an approach to avoid that, to have this, to avoid the simultaneous transmissions, which is the non-simultaneous transmission and reception mode. Okay.
Sorry, we have one question in the
Yes,
chat
please.
from Victor. Does it mean that we use two separate backup counters for two channels?
Well, that's a big question, a very good question, because this is something that we have to discuss. I mean, I have some results on that, and and in the case of simultaneous transmission and reception, yes, the idea is to have, as far as I know, independent backup counters for each channel. So basically, when we get a packet, if we allocate it to one interface, we start the backup there. If we get another packet, we allocate it to the other interface, to the other channel, and we start a different backup, which could be completely desynchronized. Will be the STR, the simultaneous transmission and reception case. In the other case, in the non-simultaneous and transmission and reception case, the idea is to define, similar to the case of channel bonding, a primary channel, and then we run the backup only on that primary channel. And in this way, we avoid this situation.
Thank you. I got it.
I will go through this in the next slide. So any comment, question is very welcome, because I think there are many things to solve on that side. So in the following, I will present some recent results. We submitted to archive this paper just last month, and it's about multilink operation. And we say it's an experimental study because, as you will see in a couple of slides, we use a real data set to test how multilink operation will work. And this real data set is obtained from several measurement campaigns that we performed a couple of years ago. In this work, we compare these three schemes. The first thing is that we consider only one access point transmitting to a single station. So this is our network, one access point transmitting to a single station. And we compare three schemes: single link operation, multi-link operation, simultaneous transmit and receive. So we can use the two links independently, and multi-link operation, non-simultaneous transmission and reception, in which the secondary link depends on the primary. The single link operation is the default operation. In the second case, the multi-link simultaneous multi-link STR, this is how we have implemented it. And there could be different implementations. In the way that we are implementing it, when a packet arrives, if the one interface is empty, so there is no other packet there, and the channel is idle, we allocate the packet to that interface. If the two interfaces are empty, but the channels are busy, so there is some transmissions in the channel, we keep the packets in the buffer. So we only allocate packets to the interface when these two things happen. It's empty and the channel is idle. I insist on this because I guess that this could be implemented in different ways, and it affects the results of how we implement these kind of things. Okay. In this example, for instance, packet one arrives to our system. The primary channel, which in our case is channel 36, is busy. So since the second interface, which in our case uses channel 100, is empty and it's idle, we allocate the packet to the secondary interface in this case. There we start the backup, and when the backup expires, we transmit the packet. Okay. Packet 2 arrives at this point. The first interface is busy. The second interface is busy and occupied by one of our packets. So basically, we keep the packet in the buffer until the first interface becomes idle, and we allocate it to the first interface and we transmit it. So that's all. Here, following previous question, basically we have independent transmissions on every link, and it works like that. In the second case, with non-simultaneous transmission and reception, we want to avoid this asynchronous case where we have transmissions starting and ending on different channels at different time epochs. So basically, we have all primary channel and we run the backup only on that primary channel. So if the packet one arrives and the primary channel is busy, basically we keep the packets in the buffer until the primary channel can start decreasing the backup, and when it expires, we check if the primary channel is idle, and it will be because the backup has expired, but also if the secondary channel it's also idle. If that's the case, as in this example, we transmit through the two channels. In this case, the packet one, because we have two packets, packet one through channel one and packet two through channel two. For instance, for packet 3 and 4, here you can see that we keep this asynchronous allocation. However, when for the non-STR, we don't get this benefit of the multiple links because we can only run the backup on the primary channel. And so packet 4 has to wait until packet 3 has finished its transmission to start the transmission process again. Okay. But I insist, the draft doesn't specify exactly how this will be implemented, and there is some discussion on how to do it exactly. In this paper, this is the way that we have done it, but probably there are different ways to do it, or maybe even better. Okay. Before I'm moving to the next slide, here
we have two questions in the queue. Sorry.
Please, yes.
Yeah, since you have allowed questions during the talk, so the first question is from Daniel. Could legacy single link APs be used in the design of centralized multi-AP.11be multi-link operation policies? Very complicated. You can read the question in the chat.
I don't see the chat. Sorry, I have the client, and I don't see how to see the chat. Let me check.
Okay, again.
I see it. No,
okay.
I found it. Could legacy single link access points be used to centralize it multi-access point? Yes, I mean, why not? I mean, and this is something that I had, one of the questions that I had in the last slide is how to combine features. For instance, one thing is multi-access point approach. So basically the idea is to build different, I mean, to allow access points to coordinate, but they can be single link. I mean, there is no need to have access point. I mean, one thing is multi-link, and another thing is multi-access point coordination. For sure, I guess that we will have access points supporting both things. But by default, we can have multi-access point coordination without multi-link. No problem on that.
Okay.
No, wait, the question was longer than this. Centralized multi-access point multi-link operation policies. So you mean, but I'm not sure what.
Daniel, could you clarify your question, please?
So I think I get the answer on my question. So that single link APIs could be used in multi-link operations, but the question, the second part of the question is maybe how to design single link APs in centralized multi-link operation without B stations.
I have, Daniel, I have no answer to that question, but I'm sure it's pretty important because we will have to deal with access points supporting multi-link, with others supporting only single link. And it's clear we will need to find policies to support or to efficiently integrate the two options. But no, I have no answer on this. But let me, however, doubt that. I have no real idea on this. But I guess if an access point supports this multi-access point framework, it's likely it will also support this multi-link. For me now, it's hard to foresee. access points that allow multi-access point coordination and not multi-link, where multi-link is easy to implement that multi-access point coordination. But if that's the case, yeah, we will have to find a way. Yeah. Okay, perfect.
Thank you.
Okay, and the next question will be from my side. So you presented some scheme from non-STR operation, and I cannot understand what is the difference between the scheme you have described and, say, the legacy channel bounding operation when we just add secondary channel if it is idle. So what is the difference?
No, that's a good point. In our example, in this case, the non-STR is equivalent to channel bonding. The only difference is that in channel bonding, you use only one interface, and what you do is to use a wider or lower channel width. Here, there are two independent interfaces, just that.
So okay, but the channel access scheme is the same.
Yeah, in this case, the scheme is exactly the same, yes.
So then I will make some comments. So in my opinion, the introducing non-STR operation, multi-link non-STR operation was done to make channel access more flexible than it is with legacy channel bounding technique. So I think this shall be somehow addressed.
Okay.
But this is not the question, it's just a comment.
No, I agree, it's a good point, yeah.
Okay, thank you.
And well, so we have in this paper, we consider only one access point transmitting to a single station using this multi-link with only two channels. So we have only two interfaces at the access point and two interfaces in the station. And to model the environment, we use a real data set, which is the WACA, or the Wi-Fi all-channel data set. Let me introduce briefly this data set. Basically, the Wi-Fi all-channel analyzer is this device here, which basically is built with 6 SDR devices, which are the warps, with each warp equipped with 4 interfaces. So in this way, with 6 warps, we are able to cover 24 channels of the 24 channels of the 5 GHz band. Okay. The idea, it's very simple. It's just to sample every 10 microseconds all the channels at the same time. And what we get in every sample, basically the energy present on that channel. So every 10 microseconds, we measure the energy on the channel. Why we did this? Because we were not able to find any other solution or any commercial sniffer or channel analyzer that was able to give us something similar. I mean, basically we could measure one channel, switch to another channel, and so on. But this was useless for what we intended. I mean, the goal of this data set, or what we needed, was to capture the correlation between channels, so the temporal correlation between channels. And this is the most important contribution of this data set. We have energy measurements of all the 5 GHz band and capturing the correlation between the channels. For instance, if some stations are transmitting using channel bonding there, we will find energy values in different channels, and those energy measurements will be correlated. So our data set is able to capture those correlations. And this is needed not for the multi-link, because indeed we are not using this property now, but in a previous work, we focused on channel bonding. And for channel bonding, that is necessary, because when you decide to access one channel, when you decide to access the spectrum, to use one or more channels depends on the occupancy, and the occupancy for sure should be, I mean, if you want to capture the real behavior of the spectrum, you need that correlation, because otherwise it's pretty useless. I mean, you cannot really use a real data set. So this was the goal of this data set, and since we had it, we decided also to use it for the multilink study. This is just an example of how we use the WACA dataset. Basically, this is a test at UPF. Here we had 3 access points, 3 clients. Here we had the Wi-Fi all channel analyzer. And well, we set some traffic load, and the access points transmitted to the stations. And basically, the result from the WACA is this kind of image here. Basically, in time, we have the occupancy of the different channels. And again, insist that the important thing here is that we are able to capture exactly the correlation between channels, which is something that, well, it's pretty unique of this data set. Just a curious result, we did some measurement campaigns in Houston, also in Barcelona, in places where we expected to have a lot of activity in the 5 GHz band, but the results, at least in average, show that the 5 GHz band is basically empty. I mean, there are some epochs of high activity, but in average it's very, very empty, or it was very empty 2 years ago. Anyway, this is just a result that we got from analyzing those traces. Nevertheless, I insist there are some high occupancy epochs that make necessary to have some smart techniques like dynamic channel bonding to really leverage the different occupancy patterns in a Wi-Fi network. Okay. So in our case, one of the measurement campaigns that we did was to put the WACA device in the Camp Nou in Barcelona during a match. The Football Club Barcelona stadium has a capacity of 1,000 people, and that day there were that amount of people, and they have 1,100 access points. They don't use channel bonding, so in this case, the data set, the channels, the temporal correlation of the channels should not exist because we have only single 20 MHz channel transmission. However, it's a very interesting data set because while in the other measurement campaigns we have basically empty spectrum, here we have very, very high occupancy values. So we have channels almost 100% occupied for very long periods of time. Indeed, if we check just the spectrogram of all the 24 channels during the time that we were measuring, we can perfectly identify the first half of the match, the second half. As you can see here, people entering the stadium, sharing pictures, videos, then they put some attention to the match, but between the first and second half, they share also data. So it's a pretty nice picture of what happened that day there. Okay. In this paper, just to analyze different conditions, what we have done is to select all the samples of the measurements of those two channels, channel 36 and channel 100, and classify them taking into account in intervals of 1 second the occupancy. For instance, 1 second of measurements, which means one measurement every 10 microseconds. So that amount of measurements is one sample of 1 second, and that sample can have 10% of the measurements busy, busy higher than a certain threshold or lower. And using that information, we classify those samples using this criterion. For instance, if they are occupied between 10% and 20%, they go here, between 20% and 30% here, and so on. Okay, and this is done for channel 36 and channel 100. Then, to test the multilink, those multilink options, the single link and the STR and STR that I presented before, basically if we want to do it to say that channel 36 is 10% busy and channel 100 is 70% busy, we pick one sample from here and one sample from here, and we run a simulation on top of those measurements. We implemented the Wi-Fi state machine and used the traces, the measurements, just to implement a kind of trace-based simulation to test what's happening, to get some results. This is for one experiment, one sample from its range, but then since we have many samples in its range, we can repeat it any times and get some more, I mean, some, let's say, yeah, more results that can be then merged and have a meaning, a general meaning beyond a single point. Okay. The first experiment that we did is throughput. I mean, if we have two interfaces, well, it makes sense to expect that the throughput will be higher. So if we compare to have one or to have two, when we have full buffer traffic, we should be able to have higher throughput when we have two. And yeah, that's confirmed with this experiment, which is pretty obvious. And the idea here was just that this is the throughut for single link, only channel 36, and this is the throughput for STR and NSTR. Nothing new. NSTR depends a lot on the state of the primary channel, which is channel 36. When the channel 36 is occupied, we cannot leverage the use of the second channel, so the throughput is low. Okay. However, when the primary channel is mostly empty and also the secondary channel is mostly empty, we can basically double the throughput. STR has more flexibility because it doesn't depend on a primary channel, so either one or the other is empty, it uses it. In that case, STR gives much more performance than single link. Okay, so those results were pretty obvious and basically confirmed what we expected. Just if you are curious, note that the CDF of the single link follows a uniform distribution, and this is because, or this is only because of the experimental setup. We have those 8 ranges from channel 36 and 8 for channel 100, and we pick the same combinations from each range, so we get this uniform distribution, nothing else. Okay, so this was as expected. Okay, no surprises. It could be interesting to see, okay, the gain that I have is that, but no surprises on that. So the idea then is to evaluate the delay. The first experiment to evaluate the delay was to consider symmetric channels. What means symmetric channels? Well, if the primary channel was 10%, had an occupancy of the 10%, the secondary channel 2, and so on. The two channels, basically the primary and the secondary, have the same occupancy, which, well, it makes somehow sense. I use this channel and I have another one which more or less have the same occupancy. To focus on delay, we have to consider non-saturated traffic, because if we want to include also queuing delay there, it doesn't make sense to have full buffer traffic. So we opted to generate traffic following a Poisson source, so pretty standard or pretty default. And in terms of load, to follow a somehow standardized way, we defined a certain fraction of the saturation throughput in single link operation. For instance, 0.2, this value here, or here, or here, is the 20% of the saturation throughput of the single link operation. For 10% is 30, the throughput of the single link is 37 megabits per second. So 0.2 is around 2 megabits per second. Okay. What I want to let me emphasize on this, that for instance, in this case, we are transmitting 2 megabits from the access point to the station, 2 megabits for single link, and also 2 megabits for multi-link. the fact that we have two interfaces doesn't mean that we increase the traffic load. So we have the same load for single link and multi-link. So the goal was, okay, if I have another interface, I have more resources, the delay should be also lower. So this is basically a motivation. And here we have the results. And the results, well, confirm that adding another interface using STR or non-STR reduces the delay. For low traffic loads, well, for low occupied channel, for medium, and for highly occupied channels. Indeed, the highest gains are obtained for medium occupied channels and also medium traffic loads, where the gains between single link, which is the blue, and the STR are one order of magnitude. So we can reduce in one order of magnitude the single link delays. This is also worst case delay. We are focusing here on the 90%, 95 percentile of the delay, but also on the average. Those lines are the average, and both the worst case and the average are reduced. So again, well, this is what we expected, so very good. Multi-link is able to reduce the delay, and we are able to quantify how much. With a single X interface, we can reduce, in this scenario, one order of magnitude the delay of single link. Pretty good, okay? However, then we ran another experiment considering asymmetric channels. The motivation was, well, I have a good channel, why not? Not very occupied, but then I have another interface, why not to use another channel? If it's more occupied than the one that I have as primary, well, no problem, I will transmit less packets there, but I want to leverage the fact that I have two interfaces. So in this case, we considered asymmetric channels. For instance, in this spot here, we have that the primary, channel 36, is 10%, but the secondary, channel 100, is 40%. Here, 10 and 70%, and here 40 and 70%. And well, we got those results. And the first thing that we got is that for some cases, for instance, for a low traffic load here, and then 10 and 40, multi-link STR gives a worse delay than single link operation. When we increase more the occupancy of the secondary channel, things go worse also. The delay of multi-link operation is even worse than single link. And this was very surprising for us, okay? Because we didn't expect this kind of result. And this is also somehow, well, when you see why, it's clear, but it's somehow non-intuitive because, yeah, I have more resources, but I get worse results, worse delay. So what's happening there? And well, if you explore what's happening, it's clear. Here, what we have is the result of one of the experiments. This is just a single case in which the delay of the multi-link is worse than the delay of the single link. In blue, we have the packet transmission, so when the packet arrives and departs from the access point. And in black, we have the occupancy epochs of the channel. This is single link, and this is multi-link, okay? 10% of occupancy means that the 10% of the time of this channel is black, and the 90% is empty, obviously, okay? And in this case, the packet that suffers the 90%, the 95 percentile of the delay is this one, okay? This is for single link, and this is the packet that suffers that 95% of delay for multi-link. So in single link, packets arrive to the access point, they go to the buffer, and as soon as possible, they are transmitted to the channel. For sure, if the channel is busy, the packets wait more than if the packets are, if the channel is empty, that they are transmitted faster. For multi-link, well, the same. As explained before, a packet arrives to the system. If this is STR, so the first available interface in the sense that the channel is idle and empty, it's the packet is allocated to that interface. And the first thing that we can observe, for instance, is that, well, there are less congestion on the primary channel because packets are distributed between the two interfaces, and the distribution is pretty proportional to the occupancy. In this case, we will have more packets allocated to the first channel than to the second one. And of course, when the secondary one is busy, we allocate more packets to the primary. And when both of them are more or less empty or idle, we distribute them through the two links. However, in our implementation of STR, we don't look at the future. Of course, we cannot look at the future, but we allocate the packets to an interface when that interface is both empty, so there are no other packets from our side, and the channel is idle, which is pretty reasonable. We detect a channel idle, so we allocate the packet there. And that's the reason why we allocate packets to the secondary interface and then those packets start the backoff there, but that backoff is paused very often and maybe paused for long periods, like what's happening here. Basically, here we have a lot of transmissions from external sources, which cause the backoff of this packet to be deferred many times, and so increase a lot the time of this packet. While this packet is here, we continue transmitting through the other link. But since we are interested in the worst case delay, this packet affects a lot, makes that the worst case delay of the multilink is even worse than of the single link operation. Okay, so even if the other packets suffer less delay, few packets suffer or may suffer much higher delay, which, if you look at this picture, I guess makes plenty of sense. So how to solve that? Well, we have to change the way that we implement STR. We cannot allocate the packet to the interface when an interface detects or is idle and empty. We have to wait, or we decided to solve this problem, allocating the packet to interface at the end of the backoff. So we get a packet, we start the backoff in the interfaces that are idle, but we don't allocate then the packet. We wait until the backoff is going to expire to allocate the packet to that interface. In that way, we guarantee that we will use the first interface open to transmit the packet, which is what is seen here. For instance, packet 3 arrives to the access point. This is standard STR. We allocate it to the secondary interface because at this point is idle while the primary is busy, but then this packet is allocated there. We cannot move it to the first interface. It starts the backoff, but then a transmission there makes that backoff to be paused, and so this packet 3 experiments a very large delay. Packet 4 arrives here. Now channel 36 is idle, so we allocate this packet to the primary channel and go on. Okay. In the new version, in the STR plus, packet 3 arrives to the buffer. We don't allocate it to the interface, we keep it in the buffer, and we start the backoff in the secondary channel. Also, we start the backoff at the primary channel, in this case, as soon as possible, as soon as it is detected idle. And then, since this backoff expires, reaches 0 before than the one in the secondary channel, we allocate the packet to the primary one, to the primary channel. Okay. However, we don't stop the backoff for the secondary channel, just in case at some point it can be reused for another incoming packet. In this case, this is not used. This feature is not used because packet 4 arrives here, and then, well, it has already this backoff active. So in case it finishes before than packet 3, it will reuse it, but it's not the case in this example. So as soon as packet 3 finishes, we start the backoff also for packet 4 in the primary. So we have again the two backoffs in parallel, and we just transmit packet 4 through the first interface that ends before the backoff, which in this case is the primary one. As you can see, the delay for packet 4 is a bit higher than just a standard STR, but we reduce a lot the delay for packet 3, which in this case was causing the problems that I mentioned before. Testing this implementation of STR, well, we get, as expected, much better results. And in this case, STR Plus is able to always reduce or always get lower results than single link operation, as expected. Why? Well, because we are using better the spectrum resources in this case. And well, this is one of the messages that I wanted to give you, that multi-link, it's a very nice idea. I think it has a lot of possibilities, but we have to take care how we implement those mechanisms, because in general, it will work better than single link because we have more resources. But as in this case, depending on how we do that implementation, on how we consider this, we can have some unexpected results. And not only in this case, but there are also many other aspects like okay, how we do with packet aggregation, how we aggregate packets through different links. Is it better to transmit many packets through one link or to distribute them through several interfaces? How we handle retransmission, because we may have transmitted one packet through one link, but then that link becomes busy. However, the other is empty. Can we retransmit packets through the other link if we have transmitted them previously through a different one, and so on? There are many questions, mostly related on how we implement it. Implement in the sense that we have the framework, but now we have to find a concrete solution, a particular solution to that. And well, it's I would say that there are a lot of things still to solve and to be able to propose specific solutions to them.
Sorry, we have several questions in the queue.
Okay.
Let's switch to the queue because you have presented
Perfect.
very interesting results. So the first two questions are from Ilya. Do you see them?
Yeah, I see them. What is the benefit of NSTR compared to channel bonding in 11AC? Ilya, I would say there are no benefit. There are no benefit in our results. The only benefit that you can see is that we are using different channels, different bands or channels that are, one is far from the other. Indeed, here in those results, we have considered only 20 megahertz channels, but we can use multi-link and channel bonding at the same time. Why not to use 160 megahertz channels in each link, and also dynamic channel bonding there? So the two things are not, are perfectly compatible. NSTR, the only thing is that is there to prevent you to keep synchronous, to prevent uplink and downlink transmissions at the same time. But basically, the idea, similar to channel bonding, is I will use all my interfaces in a synchronized way. So if I want to keep them synchronized, I have to run, to run the back of only one, or if I run the back of in multiple of those interfaces, and use the first backup that it expires, only transmit on the channels that are idle at that moment, and wait until that transmission ends to attempt another transmission. Basically that. I don't know if I answered this question.
Yes, thank you.
Okay. The second one, do you use channel traces with individual transmission recorded, or do you simulate the recorded occupants? No, we use the real data set. So we use the real traces. Basically, the simulation or the Wi-Fi state machine that we have implemented, I'm not going to say it's not, the implementation is not very efficient computationally, but we really check. So our time in the simulation is going every 10 microseconds. So we check exactly all the measures from the data set. Regarding modeling the occupancy, this is a very interesting thing, and this is something that well, I personally would like to do at some point, or somebody else, but how to capture those dynamics there and be able to build a model could be also an interesting thing. Yeah. Another thing is if the simulation is carried out on top of the pre-saved dataset, then the influence of that's a very good question. Yeah, no, you are right, Kirill. And this we had to face this not only for this work, also for the previous work where we used those datasets. Is okay, we have the dataset, but that dataset is static. So when I transmit, what happens? So I start a transmission, and the others are not aware of what I have done. Then we decided to follow two policies or two approaches. The first is the hindering, and the second is the hidden node. The second is easy to explain, because the idea is, let's assume all the external environment is a kind of hidden node for you. Okay, so you start the transmission, and then if while you are transmitting, you detect another transmission, basically the dataset says there is energy in the channel, your transmission is lost. Basically the standard hidden node problem. In that case, well, you have a lot of packets dropped, because as soon as you have some activity in the channels, you lose a lot of packets. Also, for me, that case could be realistic in some cases, but I will say that in most of the cases, the carrier sense works, and so when you transmit, the others differ. To consider this case, we applied the hindering policy that was to assume that if we manage to transmit, the others will listen that transmission and also differ, and so will not interfere your transmission. And for sure, that part of the data set, well, there were two options: just to push forward the time, just to move the data set forward, or just to skip that part. And we opted to skip that part and say, okay, this is happening here. We assume the others differ, and well, we will continue operating as the default operation. For sure, we may have, for sure, the data set in that case, if we cause other networks to defer, their load or their behavior after deferring will be different than if that's not the case. But I'm convinced that that approach is fair enough to get reasonable and representative results. But it's a very good question, and it's worth to think a bit more on that. Yeah.
Thank you. And I have two questions. So the first, my question is related to your results for light load. Could you show the slide with these results again? Yeah, with the original procedure. Yeah. So here, did you consider that if you have very light load, so your channel is mostly idle, and you have rather rare packet flow with light load, so you do not need, in this case, so if the channel was idle for a long time and the previous transmission was done long ago, you do not need to invoke the backoff.
I know. And indeed, this is something that, for instance, in this case here, right?
Yeah. So you just receive the packet and you just obtain the packet and transmit, because it seems that at light load, this effect shall somehow reduce the degradation.
Yes, you are right. And I have to say that we have not implemented that for simplicity. Here, we just by default run the backoff for every packet. But yeah, I fully agree. We could perfectly save this backup here. Basically, when you get the packet, you check if the channel is idle for the IFS or the IFS and go on. I will, however, let me say that will improve a bit the delay for sure. especially for those cases that you mentioned, that the low channel occupancy and low loads. But I will say that since that will happen also for single link, multi-link, we will get exactly. I mean, the comparison between the different schemes will be pretty similar. But yeah, it's something that we can improve and we can take into account in the future. No, however, yeah, good point.
Okay, yeah. So I think that this will affect mostly the case with the light load.
Yeah.
What will happen in high load? I think simulation is really required because it's hard to predict. But and the second comment or question is related to these two schemes, like the original and the improved one, which is plus. Yeah. So in my view, so the second scheme is maybe even more straightforward. Because multi-link operation was designed to improve load balancing between two links, and it provides very tight synchronization between two stations that operate on these two links. But there can be some implementation specific issues and some limitation caused by devices which pretend do this operation. So like for example, in real devices, we need to prepare a packet for transmission, put it in some buffer, and then once backoff is counted down to 0, the transmission occurs, so we do not have any control of this packet anymore. And the question is, do you know some limitations of the devices that do not allow using this STR plus scheme?
I don't know. That's a good point, and that's why I mentioned it later. What you say, that there are some specific implementation issues that may prevent implement some features or others, or to force you to do something in a given way. We are not much aware of implementation details. This is just a proposal, assuming everything is possible. I mean, everything. It doesn't look too complex, but we did not introduce or take into account any kind of constraint. On that line, for instance, something that I will say it's also important is things. For instance, this STR plus mechanism. I'm not sure if it's fair. I mean, fair from the point of view of Wi-Fi, because we are running, for instance, parallel backups, and we are reusing one backup for a packet that may arrive later also. So beyond only implementation things, we have, I mean, those mechanisms have to check, or maybe have to take into account fairness and other kind of things like that.
Yeah, sure. Thank you.
You are welcome. No, perfect. And well, I'm almost at the end. So just to finish, a couple of slides of multi-access point coordination. This is, I will be very brief here. Just to say that, I said this before also, multi-access point coordination, the idea is to reduce contention between access points that belong to the same network and improve the way that the resources, the spectrum is used. Somehow it doesn't make much sense that you have a network with multiple access points and they compete between them to get access to the channel. So why not to provide a mechanism that over the air allows them to coordinate their transmission? So if we manage to do that, everything should be better or should work better. For sure, to do that, we need some extra overheads, extra coordination overheads, especially if we do over the air. If we have a wired solution, that's another thing, but over the air, it means more overheads and more complexity, because, well, the mechanism to enable this coordination, or especially these joint transmissions and the use of resources, well, require take more things into account to work. There are several proposals. The ones that look like will succeed in the sense that they will be included in the 11B are well, just temporal coordination, spatial reuse, coordinated spatial reuse, and coordinated to FDMA. 11AX introduced already spatial reuse, but in this case was decentralized. So basically, a device that listens to transmission can reuse that transmission opportunity, but in a very conservative way. So if the two access points or the two nodes that can transmit at the same time agree in advance which power to use and which duration and whatever, probably it could be done in a more optimal way, so we can achieve higher rates and better performance. And the same for FDMA. I mean, somehow, if we can distribute the resources in a coordinated way, the same, we will be able to allocate channels or the best channels to the best stations at every moment. Okay. Other techniques, which like coordination beamforming, null steering, and these kind of things, could be also implemented. They belong more to physical layer, which makes them more complex in the sense that they require more information, especially the channel state information of all access points and devices to be implemented. Joint transmission is nothing else than distributed multi-user MIMO, which has been in the research focus for many years. But basically, they require a very tight coordination, tight synchronization between the different devices, which makes them very, very complex to be implemented. Beyond those techniques, multi-access point coordination also can help to solve this problem. For instance, I started this presentation with this slide. In this slide, we have these 3 access points contending for the channel. But if they can coordinate their transmissions, for instance, in this case, that access point 1 wins the contention, it's likely that it allows, for instance, access point 2 with the lane sensitive packet transmit earlier than the others. For instance, here, what we have is that access point 1 wins the contention, so it exchanges a packet with the other access points from the coordination group, from the group of access points that have agreed to do some coordinated actions. It gets information from those access points, for instance, the buffer status, plus some other channel state information or whatever. And then this access point that has won the contention, which could be the sharing access point, may decide how to schedule the rest of transmissions, giving priority, for instance, for the transmission of access point 2. If a spatial reuse is supported, or also FDMA, we could have perfectly the 3 transmissions at the same time, just here exchanging exactly which resources will be used by access point 3, by access point 1, and access point 2. So avoiding colliding and any kind of interference between them. So in that sense, multi-access point coordination or chop sharing, which at the end is chop sharing option, also enables what is kind of with this kind of global scheduler. I mean, we can schedule transmissions not only from our network, our BSS, but also from other BSSs in the same network in this case. So it's a very interesting option for future Wi-Fi networks. And this is my last slide here. So just to conclude, this table summarizes the new features from 11B, both the ones that extend 11AX plus the ones that the disruptive ones like multi-link operation and multi-access point coordination. And what's next? So well, there is a lot of things still to do in all of those topics, but assuming that we have everything working for Wi-Fi 7, from the research side, we have to see how to optimally use them. We have to find solutions to proper use each of those features. They are becoming very complex, which is very positive because it means that we have to think how to use them. But it's not yet clear which is I mean, which is the best solution for each individual case. And even less if we consider them all together. I mean, if we have, as you asked before, if we have multi-access point coordination, multi-link operation, and the multi-access point coordination with a special reuse and OFDMA, but not all the access points or not all the stations support this, things become very, very complex. So yeah, there is some room to find ways to get the most of them. And there is where maybe, I'm not fully convinced or yet sure, maybe machine learning can help. Basically, machine learning is to get data which could be results from previous actions and find patterns there or find some indications of what to do next, for instance. And in that side, basically seen without human intervention, which is that what machine learning allows, just to do it automatically, we can find ways to optimize the different features that we have there. Okay. And just to conclude, maybe not yet, but maybe yes, I don't know. Maybe it's time to think about what will with Wi-Fi 8 will be. We have to think if it will be just an extension of the requirements, more rate, more throughput, lower latency. It will add some other disruptive features. For instance, I'm surprised, well, not surprised, but I know that it has been discussed, and I also know it's something that you have been working on that. What do you think? NOMA will at some point appear in Wi-Fi or full duplex transmission in the same channel? Are features that could appear at some point, not, whatever. We have to think a bit on that side. And also following the same comment as before, and following trends also in 3GPP, we may have to extend what is the Wi-Fi architecture to support machine learning, in the sense that we want to optimize the network or to allow self-optimization using those kind of techniques, which may help to adapt or to particularize different solutions for different scenarios. At the end, we have plenty of different scenarios with more nodes, different traffic profiles, different requirements. And the key somehow is to be able to tune the different options to fit the characteristics of each of those cases, of each of those scenarios. And that's all from my side. Here you have some reference that we use it through the talk. And yeah, thank you very much for the time. I think it took more than I expected, but I hope you got some positives from what I have said. And yeah, if you have more questions, more things, I will be happy to keep this discussion.
Thank you, Boris. So, yeah, we have a lot of questions in the queue. So the first question is from Ilya. Do APs out of reach of each other benefit from being in the same AP group?
Well, the first thing here, I mean, one of the things I mean, the multi-access point coordination gives you a framework, but then the first thing is to define how you create those groups. By default, what I will say is a group should be, I mean, all the access points on a group should be able to see each other, to be able to talk. Say that it's true that it's possible that, for instance, if the sharing access point is able to see all the others, it can somehow coordinate the different access points. And basically promote a special reuse. Or if two access points don't see each other, they can transmit at the same time and go on. So, but I have no answer, in the sense that yes, they can benefit, but there is a lot of things to solve there. I mean, because we need to learn how to create those groups in an optimal way. Also, I mean, this multi-access point coordination implies that the access points see each other, but also use the same channel. You could say, but I mean, just put access points, nervy access points on different channels. Why? I mean, why to have them on the same channel? Well, channel allocation, channel bonding, multi-access point coordination, all those things have to go together, basically. And yeah, this is an open challenge.
Thank you. So the next question is related to hybrid RQ. The questions from Ruslan. Not yet clear if hybrid RQ is robust against collisions. Sorry, but doesn't that mean it's an open direction?
No, I would say no. I mean, I will not. For me, hybrid IRQ is pretty an old topic. The only thing is, as far as I know, it has never been considered for Wi-Fi. Although there are many papers doing it, I mean, in trying to evaluate the benefits of IRQ on Wi-Fi. I'm not aware of that. I mean, I'm not aware. I mean, I don't know what the results they have, and this is a topic I have to say I have no more information. So, but no, it's not well, it's not an open direction. Maybe yes, but I'm not familiar with it, so I cannot say much. Sorry.
Okay, thank you. There is a comment from Ilya. He's not sure if hybrid RQ is still considered for 11BE, and I support this idea, this comment, because there are a lot of implementation issues related to hybrid RQ in Wi-Fi, but the gain of hybrid RQ is not clear.
I will have to date then my info from 11B. It could be outdated. That's true. That's true.
Yeah, it was discussed. You're absolutely right. It was discussed, but as far as I understood, so the group switched to some more clear solutions, which definitely will provide benefit, like multi-link, which you have described and studied.
Well, that's in line with what I said about the IRQ, that it's not clear. That's a good. I mean, I think it makes sense. Let's say that a step forward. So not consider maybe IRQ without more information about.
Question from my side. So, what changes does AI or machine learning require to be done in the spec of the Wi-Fi protocol?
Oh, that's a very
actually.
hard.
I'm not sure that it shall be done. It shall be somehow standardized, because it's typically vendor-specific solution. AI-based solutions are typically vendor-specific, and they do not require any modification in the specs. So that's why they were not considered by the group before, by the to the learning group. But maybe you have some more information, some more ideas on this topic.
No, not really. I mean, maybe as other mechanisms, from the specifications, you can define some interfaces or some ways to plug those mechanisms. But it's likely they can be just implementation. I mean, they can be related just to implementation. No, not sure. I have no answer also to that, because it's pretty hard. If in any case, I agree that if the specification moves to include some of those features, I guess it will just limit to specify some interfaces or something like that.
So the next question, would artificial intelligence or machine learning seem interesting for vendors? Would not it be too complicated for cheap Wi-Fi devices?
That's also a good question. Yeah, it could be too complicated. It depends on what we have in mind when we say machine learning. If we think about deep learning, where we have a lot of data and things, yeah, I mean, it doesn't make much sense, at least to have it inside the interface. If we think about simple algorithms more related to reinforcement learning with not so big state space, I think they can be implemented. Another thing is that the gains that you can get justify that. But yeah, and also I mean, we have some results that implementing some algorithms, some machine learning algorithms, you get benefits for sure. But maybe you can also implement an heuristics that uses some statistics or some measured statistics that gets better results. So it's a field to explore. I'm not saying, or I will not say that machine learning is the solution for all the problems in terms of performance, but it's somehow it's interesting, especially because it provides a set of tools that allow the mechanism to adapt to the different conditions in a way that you may have not thought before. However, to support that, you may be less efficient than if you try to think in advance all the cases that may happen there. So sometimes I say that machine learning is for lazy guys. Why? Well, because I don't want to think what will happen. I put machine learning there and I leave everything to the algorithm to solve. So, but it's pretty interesting, yes.
Thank you. The next question is from Victor. Thank you very much for your talk. If I got it in a correct way, at the beginning of talk, you mentioned that machine learning techniques can be utilized to improve the work of channel bonding techniques. Could you give an example of how machine learning can be utilized for channel bonding?
Well, I think that, well, basically in channel bonding, at every time that you have to access the channel, you have to decide, you have to decide. In the dynamic channel width, you pick always the maximum bandwidth that is available. However, this is not necessarily the best solution. I mean, maybe if you have 4 channels, or you are operating on an 80 MHz channel, and your primary is in the leftmost channel, maybe it will be enough to pick only 40 or even 20. Why? Because if you pick 80, maybe you are causing some interference, or you are making other networks to defer, which somehow causes the other networks to contend harder in the future. So if you don't need 80 MHz, why not to use only 20 or 40? However, this is how to learn that. So maybe then you can plug an algorithm, a machine learning algorithm there, which basically explores the different options, rates them, and chooses the best one. For instance, this could be a simple case of applying machine learning there.
Okay, thank you. The next question is from Dmitry. New features of .11be increase the throughput mostly in extensive way, like usage of 320 MHz, higher order of MIMA, multi-link. How will it affect the energy consumption of the devices? What can be done to avoid making it too high and still to have benefits of Wi-Fi 7? So what about energy consumption?
Well, I have no results. No, I haven't thought much on that, except that I fully agree. Indeed, for the multi-link, okay, it's super nice. You have multiple interfaces. Our results are with 2, but why not to have 4 or 8 interfaces? I mean, it's at the end, if you want to have all of them active and so benefit from these features, you need to consume energy. So it's not, it's a big problem, especially if you are using a battery-powered device. For the access point, maybe not so much, but for the battery one, yes. And yeah, you need to deal with that. For instance, you can for instance, I mean, you have TVT or target wake time in 11AX or 11AH that you can leverage these kind of things also for the multi-link. If you agree with the access point when you will wake up or which interfaces you will wake up to transmit, maybe is a solution for this kind of, for dealing with higher energy consumption. But again, link it with the previous comments. I mean, if we care about energy consumption, probably we will have only one interface, and well, it depends. If we have cheap devices like sensors, for sure we will just have one interface, and then the problem is how to integrate those devices with a single interface in a multi-link network in general. But also I agree, if you have even a laptop, whatever, with multiple interfaces, you also care about energy consumption. So then is where we will have to think how to get the most from these new features and minimize the energy consumption, which again, I guess it means to leverage DTIC or other power saving mechanisms already defined, or that will be defined in future in the Wi-Fi community. Linked to that, we have not mentioned it today, but it's clear that Wi-Fi is giving a lot of power to the access point. I mean, basically, we are moving from a fully decentralized operation to a more or less centralized one, with the access point controlling or scheduling both downlink and uplink transmission. There, we can have an opportunity to leverage both this multi-link and energy consumption. For instance, if we can in advance predict when we will have traffic transmit, well, we can decide which interfaces are turned on, off, whatever. But yeah, it's a very interesting thing. Yeah, and I have no answer at all.
Thank you. And I think the next question will be from Professor Stefanuk. You did not manage to write something in the chat, but I remember you wanted to ask something.
Thank you very much. Thank you. Boris, I mentioned that we have developed some schemes for the mobile communication. I mean, telephone mobile communication, where we have a lot of channels and all of them interacting. And this interaction creates special features. And when, for instance, in one channel there is some transmission, then this useful transmission in this channel could be very wrong for the other people, because other people will obtain like a noise, and the noise could be. And in this case, the learning was used, and it was very useful, and it's very simple actually. It's very simple formula. It could be implemented if you understand what you would like to obtain. It's not so. But also, you mentioned this artificial intelligence that is your future interest. Artificial intelligence also is used there, because even understanding the content of the transmission could be used to improve the communication.
Okay.
And so, Boris, I just I don't know how to contact, but I think that we'll ask some of my colleagues in my institute about your address, and maybe we'll send you some contact for me.
It will be a pleasure.
If one day you decided to do this, also.
Here you have my address. I'm easy to find anyway.
Yes, I see it. Yeah.
But yeah, no, I will be happy to share, to get in touch with you or with anybody and and discuss any of those things. Yeah, sure. Thank you.
Yeah, I'm an artificial intelligence specialist as well. So maybe I'm vice chairman of the Russian Association for Artificial Intelligence, and I am the member of the European Artificial Intelligence Association. So it's a quite clear area for me.
Okay, then perfect. Sounds very good. Yeah.
Okay, and thank you. Thank you for your presentation. It was very understandable. You know, usually when I have the presentation, this seminar, I'm a bit lost because of the many terms used that I would never understand what these terms are about.
Yeah, it's a hard area.
In your presentation, it was okay. I had no problem.
Thank you very much for that comment. I appreciate it.
Thank you. I thank the chairman of the.
Thank you. Any other questions to Professor Bellalta? So thank you very much for the very interesting talk. I think it was maybe the longest talk on our seminar, but it was really very exciting, and we have, I think, very interesting discussion and very useful.
And thank you very much for inviting me and the opportunity to chat with all of you. I enjoyed a lot this talk with all the questions, comments, and that's great.
Thank you. I would like to thank all participants for a very interesting discussion also. And that's all for today. And next time we will have the talk by Professor Periklis Chatsimosios.